Okay, why don't we get started? This is week 4. This is the final hour of class, and I thought I'd do it online. This classroom here is about 40 degrees today, so I might be jumping around quite a bit. So I want to talk in this little segment about mediation and moderation. I think it's a term, those are terms that are used all the time, especially by developmental psychologists. They're completely foreign to economists, even though economists do the same sort of thing. They just have different names for it. There wasn't really a good reading about this. It's not going to take long to explain it. SEM models. A number of you have either already done SEM kind of models or will soon learn them, are an example of a mediated model, right? So I wanted to make the connection between applied regression, which is what this class is about, and SEM models. But let's start out with this basic distinction between moderation and mediation. Moderation is about exogenous variables. Remember, exogenous variables are those that are causally prior to a variable of interest, X in this case. Exogenous variables that differentiate effects of some X on Y. Okay, so in the regular part of class, we look to see whether the effect of family income on children's completed schooling differed for Blacks and whites, or Hispanics and whites. That's all about moderation, right? You've got some exogenous variable, race, ethnicity, and you're investigating to what extent that exogenous variable differentiates the effect of X, in that case, family income, on outcomes, which in this case was completed children's schooling. Moderation. Mediation is all about endogenous variables. That means variables that are causally subsequent to the X variable of interest. Endogenous variables that account for the effects of X on Y. Okay, so exogenous differentiation, endogenous accounting for effects. So let's talk about those two things. We won't have that much to say about moderation. SEM is all about mediated models. And moderation is just about interactions. So we've already seen how to run interaction models. So we've done, in effect, moderation. The way that moderation is sometimes depicted, right? We've got some X variable affecting some Y variable, family income and children's education, for example. And then we've got some moderator, Z, in the case earlier, it was race, ethnicity, and we're saying that there's the possibility that the effect of X on Y, this path, depends on Z. Mediation is all about instances where we have an X variable affecting a Y variable, and we're trying to account for that effect with some Z variable. All right, so the effect of X on Y might be explained to some extent by Z. So that's a difference in the way these things are presented. So let's move ahead with moderation. Let me set the board up here. So I'll do a little pause. Okay, so we're going to put off mediation for the time being and focus on moderation. Suppose we've got some treatment, some experimentally allocated treatment, or we're pretending that family income in that example was randomly assigned or approximately randomly assigned. So one way of trying to clean up omitted variable bias is to add a bunch of controls, and that's often done. So the actual equation that we would run would be the outcome in the case of the children's education. This was completed education. The treatment was $10,000 of family income, additional $10,000 of family income over 15 years. And then there were a bunch of other controls. Suppose we run that regression, or suppose we run some experiment. That's probably a more intuitive kind of way to think about it. Suppose we run an experiment. People are randomly assigned to the treatment group or the control group. We put in some other controls because there might not be balance between treatment and control groups, even though we had random assignment. Suppose our estimate of B1 is 0. Suppose we can't reject the null hypothesis that B1 is 0. Disappointing, very disappointing, especially if the experiment took quite a while to develop and gather data for. What often happens, you see this all the time, people do experiments of various kinds. They run this regression, and this you could think of as a main effect of the treatment. So main effect is 0, but then people say, well, maybe there are subgroups for whom the experiment was successful. All right, so they start looking for moderation. Are there characteristics of the sample, exogenous characteristics, that differentiate the effects of the treatment on the outcome? All right, so there might be some subgroups for whom the treatment is positive, and they launch a search for those subgroups. So you see it all the time. Sometimes articles don't even say, they can't admit that the main effect was 0, and they just launch into a subgroup, and they've got theory about why this experiment should be important for the subgroup and show that it is, and then they're done. What are the problems with this? There are 2 problems. One is that if you don't pre-register your expectations or hypotheses for subgroup interactions, in other words, the subgroups that are going to be showing experimental impacts. So unless you commit to those beforehand, your search for interactions may turn up ones by chance. All right, so if you engage in a search for 20 different interactions, 20 different kinds of moderation, 20 groups, and do a p less than 0.05 test across those 20 groups, you'd expect one to show up just by chance. It's not real, it's just going to show up by chance. So it's best to commit yourself to what particular subgroups you're going to look at, either implicitly or explicitly through pre-registering your study. And then if in fact one of your pre-registered expectations comes up as being significant, it's more believable. Okay, so that's one problem. Another problem is If main effect is 0, think of a main effect as kind of an average effect across the entire sample, then a positive effect for subgroup A means that there are negative effects for other subgroups. All right, that just stands to reason. If a main effect is just an average effect over all groups, and then you identify one group where there's a positive effect, there have to be other groups where there's a negative effect to balance it out. And again, people aren't usually very forthcoming in admitting this. And I would argue that doing a study where you find a main effect is 0, you identify a positive effect for a subgroup, if you don't spend as much time theorizing about the subgroup, maybe subgroups with negative effects, as the subgroups with positive effects then you are not conducting an honest analysis. Right? An honest analysis is really one that's complete and attending to all the important parts of the topic that you're investigating. And if you just have a main effect at 0, find a subgroup where there's a positive effect and totally ignore the possibility that there are indeed subgroups and don't think about how this treatment could actually produce negative impacts on a group. If you don't spend much time on that, thinking about that, writing about that, then you really aren't being honest in your analysis. And it turns out to be very important. One of the findings in the early childhood education literature, there are very few early childhood education evaluations that offer education to the general population. They're usually offered to a subset of the population, disadvantaged children. But in some cases, they've been offered to everyone. Pre-K programs, state pre-K programs are an example. And it's sometimes the case that those pre-K programs have a very small or even zero total effect. People estimate effects for the disadvantaged subset of the sample and may sometimes find positive impacts for the subgroup that is characterized by, say, economic disadvantage. But then they totally ignore the fact that that means that relatively advantaged kids may actually be hurt by the treatment, in this case, the preschool. And it could well be that if advantaged kids are not going to the preschool, they might have options because their parents can afford them of more private education programs, alternative to the state pre-K program, or not attending any program at all and being home. Those may be superior, and that's why the effect of the pre-K program is negative for them. There were better alternatives that they were foregoing. So that's, you still might want to go with that program, but policymakers should know that there is this trade-off between this program advantaging some kids but disadvantaging others. So it's important to be honest about the fact that you may have a treatment that is positive for some groups, but is actually negative for others. Okay, so that's it for moderation. Let me set up mediation. Okay, mediation. Mediation is the kind of model that SEM works on, and it is characterized by these endogenous variables Z that are hypothesized to help account for the effect of X on Y. Mediated models are sometimes called causal models. Which may be confusing because we had talked about the notion of causation. But in this case, there's a distinction between statistical causal models that's what we've talked about up till now. That's when you have a model that's delivering to you a causal impact, which is this difference between the value of an outcome for individuals who were both, well, the counterfactual reasoning here. An individual has an outcome in the presence of a treatment and in the absence of a treatment, and that difference is the causal impact of that treatment. That's what a statistical causal model is all about, and that's not what mediated models are all about. There are conceptual causal models. And that's what mediated models are about. So what that means is, suppose you've got some treatment. We're doing this experiment for families with very young kids. We're giving moms $4,000 a year in monthly payments. We're expecting that X, that treatment, to affect child outcomes, things like cognition, socio-emotional behavior. And we can think of all sorts of potential mediators, all sorts of pathways, causal pathways. And that's what mediation models are all about. So the effect of that treatment, that income increment on some child outcome may be accounted for by what parents spend the money on, right? Are they using that money to buy things for their children, books, higher quality childcare? You can think of all sorts of things that they could be spending that money on. So that's one kind of causal pathway. That's one set of Z variables. But another set has been hypothesized through kind of a stress process. So a benefit of higher income is that parents are less stressed because they can handle all the difficult parts of trying to juggle family life when you've got young kids and you've got to work and so forth. So those mediators are things like depression, like anxiety, like parent sensitivity, how responsive is a parent to a child. So those are more Z's. And the idea is that, in theory, you'd really like to have a complete understanding of how your particular X variable, in this case, the income treatment, is affecting the child outcomes. You'd like to have a whole set of mediators that collectively account for all of this effect of X on Y. So it's a causal model in the sense that it lays out the conceptual model behind why X should affect Y. And it does so explicitly by including these Z variables. And some models estimate these kind of quote unquote causal models. They do so with attention to the measurement characteristics of X, Y, and Z, which is not something we really will spend much time on this quarter. So they have a lot of advantages, but what I wanted to try to emphasize is that at its heart, this mediated model is really just a couple of regression models. And you can take the regression tools that we've already developed and apply it directly to this kind of model. Okay, so let's do that. When we see a model like this, it's really two equations. There's an equation, one equation for every variable that has arrows running to it. All right, so here we've got two variables with arrows running to them. Let me get my notation here. Z is one of them. So one equation is Z equals some constant. We're going to kind of ignore the constant, plus C1 X, right? The only thing that's predicting Z is X. So this is the equation associated with that. Z equals some constant plus, in this case, we're saying C1 is the coefficient, C1X. And then we've got a second equation where the dependent variable is Y. And we can estimate that Y is some constant plus. So we'll label this C1. That's the path running from X to Z. And we're going to say we've got D1Z. So Y is a function partly of Z. So this is D1. And then it's also a function of X. We'll call this D2. Okay, so this this actual system of equations, it's represented by this model, really reduces to one equation per endogenous variable where things are have arrows running to it, Z and Y set up this way. Okay, so one thing to notice let's plug, let's say this is equation 1, this is equation 2. Let's plug 1 into 2. And that gives us y equals some other constant plus d1 times z. What's z? Well, z is a constant. Constants are annoying. Plus c1x. Right? We're just plugging in z, and then we'll keep going. Plus d1z plus d2x. Okay, so let's ignore the constants. That's y equals d1 c1 times x plus okay, so sorry. The nice thing about recording is that you can pause. Okay, so you can pause, but you can't easily erase. So I screwed up here. I plugged in the value for z, which is from this first equation, but then I repeated it over here. So let's take this out and just put d2x here. And then we've got y is this constant, which we're ignoring, plus d1 c1x plus d2x. Okay, which is just y equals d1 c1 plus d2 x. All right, so compare this mediated model to just this simple non-mediated model where you've got x predicting y. All right, and let's call this coefficient b1. So we've got y equals constant plus b1y. That's the total effect. Of x on y. All right, so now we can decompose that total effect. See this, y is a function of x. Y is a function of x for total effect, and y is a function of x for this mediated model. And what you can see is that the total effect of x on y, right, which is b1, equals the direct effect of x on y which in the mediated model is d2 plus the indirect effect of X on Y operating through Z. All right, so that's D1C1. All right, but I mean, to see it more clearly, just look up here. We've got the total effect of X on Y consisting of this direct effect, D2, plus this indirect effect, which is the product of the path running from X to Z times the path running from Z to Y. All right, so if you run these two equations and plug things in, you'll come out with a total effect. In other words, if you add up D plus C1 D1, you'll get exactly the same coefficient as if you just regressed Y on X. All right, so that's all a mediated model's doing. It's taking some total effect and decomposing it into an indirect effect through the mediator of interest, and then everything else, what's left over. That's D2 in this case. So that's useful. You know, in theory, you've got some causal model that is positing a Z, or usually a bunch of Z's, that are accounting for the effect of X on Y, and you'd like to see where the action is. And this provides a way of giving you an idea of where the action is, because you want to be able to estimate the indirect effects and see which indirect effects, if you've got a bunch of Z's, are most important. And you'd really like to have these indirect effects be large relative to whatever's left over. I mean, what's left over is kind of an admission that you really don't know important things about how X is affecting Y. You might know that, well, part of it is explained by Z1, part of it is explained by Z2, but if most of the action is still left over after you include all your mediators, then you're stuck not having most of the action explained by your mediated model. So let me pause and set things up again. Okay, so I did a bit of erasing. This kind of logic where the total effect is decomposed into a direct effect and an indirect effect that worked in the case of one mediator is exactly the same as if you have multiple mediators. So here we've got same X affecting Y, but instead of one Z, we've got two Z's. The path model, the SEM model, would allow for paths that run from X to Z1 and X to Z2, as well as paths running from Z1 to Y and Z2 to Y, right? And we've got a direct effect left over here. But this basic logic of a total effect, which in this case, take out all the Z's, just regress Y on X, is going to be equal to the direct effect, which is this path from X to Y controlling for Z1 and Z2, plus now two indirect effects. One indirect effect is operating through Z1. That's going to be the product of this path and the product of this path, plus the indirect effect operating through Z2, which is the product of this path times the product of that path, right? So you can go through this calculation where you've got a total effect. You want to see to what extent Z1 is a more important mediator than Z2. You want to see to what extent both Z1 and Z2 are important mediators relative to what you can't explain through mediation, which is that path number 3. So it carries over this logic to many, many mediators. All right, so what's important to note here about these mediated models? One is that indirect effects involve the multiplication of 2 paths, of the coefficients on 2 paths. All right, and so because you multiply these paths together, you can often get rather small impacts. So let's go to a much simpler example. We have X, we have only one Z, and we've got Y. All right, suppose, and it's often the case that these variables are all standardized. Suppose we've got, we regress Y on Z, and we get a coefficient of 0.4. We regress, well, our regression is going to be Y on both Z and X. We can see the coefficient on Z, let's say it's 0.4. We can see the coefficient on X, let's say it's 0.25. That's one equation. The second equation is regressing Z on X. And suppose that's 0.1, 0.4 also. All right, so these are just examples. So it looks like we've got a pretty big indirect effect, right? We have only 0.25 standardized coefficient down here and 0.4 coefficients up on the 2 paths for the indirect effect. But the indirect effect involves the multiplication of the 2 paths, right? So the indirect effect in this case is the product of 0.4 and 0.4, which is 0.16, which is considerably smaller than the direct effect, which is 0.25. So what often happens is that you can have structural equation models that are much more complicated than this. You can have X, you can have a Z1 here, you know, a Z2 here, a Y here, and maybe a Z3 here. Maybe Z1 has a direct effect on Y, and Z2 had an effect on Z2 also. So you get these very complicated kind of path models. And people estimate these things, and oftentimes they get really big coefficients, standardized coefficients. But let's say you want to know effects of X on Y operating through Z1. Well, you're getting the product of these coefficients, and you're getting the product of this coefficient times this coefficient, all the kind of arrows that are going to Y. So even though the individual coefficients on these paths can be substantial and quite significant, if you really want to know how important they are in terms of mediation, that's a function of the product of these paths, which is often a pretty small number. Another example of indirect effects comes from skill building models, right? Let's say you're interested in how kids build up their math skills. Math, we know, is a progression from very simple skills, knowing numbers, knowing ordinality, to knowing addition, to knowing multiplication and division, to fractions and so forth. And it might seem, let's say we've got skill 1 in preschool, skills 2, skills 3, skills 4, skills 5. So we have, over time, a measurement of these math skills of kids. And they have linkages. And we want to know how effective would it be to have some sort of intervention that would boost S1, preschool skills, let's say, preschool math skills. If only we can start kids out on the right trajectory, they're going to be better at math at a year later, 2 years later, 3 years later, and 4 years later, right? So we might think that a effective intervention to boost early skills is going to boost skills 5 years down the line. Well, if you really want to know what the effect of S1 on S5 is, you've got to estimate these linkages, right? And suppose they're 0.6, pretty big, for every pair. If you want to know the effect of S1 and S5, you have to multiply 0.6 times 0.6 times 0.6 times 0.6, right? Which is 0.13, which isn't so big. And if you actually estimate a model like this, you get numbers that aren't as high as 0.6. It's more like 0.4. And if you multiply 0.4 times 0.4 times 0.4 times 0.4, you end up with 0.03. So bottom line is, even though each of these linkages can be fairly strong, the overall linkage between, in this case, S1 and S5 is going to be the product of these coefficients. And that can get pretty small pretty fast, right? So saying it's 0.6 or 0.4 means that, that early skills are important for subsequent skills a year later, but there's a lot of other stuff that turns out to be important as well, other kinds of things that are happening to kids. And the same thing here, the same thing here, the same thing here, the same thing here. So if you're looking at indirect effects, it's important to know that they multiply together. That's point 1. Point 2, I will set up. Okay, this last point about mediated models. Just because you are estimating a structural causal model, all right, we said mediation is a kind of causal model because it's showing the process by which, in this case, X affects Y. But just because you're estimating a structural causal model doesn't mean you can ignore statistical causation. Let's say statistical causation complications. All right, so this is a very important point. People will estimate these mediated models and they'll get numbers for the paths and they'll talk about the importance of Z in accounting for the effect of X on Y. But unless they've got a causal effect of X on Y, what good is it, right? They're just looking at associations. And as we talked about early on in the class, if you really don't have some way of producing fairly convincing causal estimates with control variables, with an experiment, with a quasi-experiment, you're kidding yourself if you're really thinking that you're estimating causal effects. Might be a causal model in a structural sense, but you still have to attend to all the omitted variable bias and all the other kinds of potential problems when trying to estimate the causal impact of anything on anything else. So even if, let's suppose you have random assignment for X. All right, so that's a huge plus, right, for getting close to a causal model. Random assignment is going to give a plausibly causal impact of X on Z if you just regress Y on X and forget about Z, in other words, get the total effect. That's going to be arguably causal if X is randomly assigned. But these other paths aren't causal at all, right? So think about the path running from Z to Y. You might have totally nailed down the effect of X on Z, but you didn't randomly assign Z in order to get a causal effect of Z on Y. So this path, let's put it in red here. Path number 2 is potentially subject to all the omitted variable bias that might happen with correlated data. You need to think about other control variables that you'd want. And similarly for this path here, even though X is randomly assigned, if part of what's going on to give you this, this coefficient involves a non-experimental link between Z and Y, you wonder about whether this is a reasonably estimated direct effect. So totally nail down total effects, totally nail down part of the indirect effect, but you can't be certain that you've really nailed down causal estimates of mediation unless in some way you have identified an effect, causal effect of Z on Y. And just a second point along the same lines. You'll often see articles that will estimate a mediated model. There'll be one mediator, and people will look to see whether this is significant and that's significant, and if so, they'll claim significant mediation. But if you think about this, suppose in fact you've got a bunch of potential mediators, a bunch of potential variables that are accounting for the effect of X on Y. And that's usually the case, right? There isn't just one mediator, there are several different pathways. If you leave out all these other mediators and try to claim mediation with one mediator, the mediational path that you're going to estimate is going to pick up not only whatever influence there might be from Z1, but it's going to pick up whatever influence there is through these other Z's that are correlated with Z1. It's a standard kind of omitted variable bias where if you haven't controlled for all of the correlated predictors, then you really haven't gotten a very interpretable impact. So if you are estimating a mediational model, you really need to estimate the effect of any particular mediator controlling for all the other mediators, in the same way that if you're trying to estimate the effect of family income on completed schooling, as in the first article that we examined, you can't make much of a claim for the effect of income on children's completed schooling being anything close to causal unless you've controlled for other independent variables like parent education, like family structure, and so forth. So omitted variables can be just as much of a problem in these mediated models as they can in all the other models that we've been talking about.